Hello, everyone, and welcome to this episode. I'm Aaron Rudolph, and this is AP Chemistry, Section 5.4, all about elementary reactions. In this video, we're going to be learning what an elementary reaction is, how we can use it to write a rate law, and then we're going to look at some questions that are very similar to questions you're likely to be asked on your exams. So grab a pencil and let's get started. As we often do, let's take a look at the learning objectives for this episode. Represent an elementary reaction as a rate law expression using stoichiometry. That's going to be key for us. The rate law of an elementary reaction can be inferred from the stoichiometry of the particles participating in a collision. We're going to start with that collision word. That's very important. Elementary reactions involving the simultaneous collision of three or more particles are rare. That's what we need to know. And so let's look at a few examples. Let's talk first about collisions. Okay, it might make sense to you that if two molecules are going to react with each other, maybe they're exchanging protons, electrons, or just parts of themselves, they probably have to collide with each other. And that is true. So they can't react from across the room, they actually have to hit and collide with each other. And you can imagine molecules colliding, sometimes more frequently, sometimes less frequently, depending on things like temperature and concentration. But basically, it's all about collisions, right? But not all collisions are successful collisions. Just the fact of two molecules bumping into each other doesn't necessarily mean that they're going to react. In order for a molecule collision to be successful, the molecules must collide with enough kinetic energy to overcome the activation energy and produce new products or intermediates. So just a gentle bump is probably not going to do it, but if they slam into each other hard enough, they may pop off part of themselves and jump onto the other molecule, or they have the energy to trade their electrons and protons and things. Okay. They also must collide with a favorable orientation that allows the transfer of atoms from one molecule to another molecule. Okay, so let's look at a couple of examples. So for example, if we wanted to imagine taking a carbon monoxide, which only has one oxygen, and add an oxygen to it to make carbon dioxide. Well, if the oxygen molecule that's there supplying the extra oxygens hits the other oxygens, it's not going to do anything because that's not the place where it needs to latch onto. But if we turn the CO molecule around, that oxygen can come over, combine, and we get some carbon dioxide being formed. So there's often a business end of a molecule and it has to hit the other business end of the other molecule. And if they don't, reaction's not going to happen. Also, molecular speed plays a part because if you have something with not enough kinetic energy, they might collide, but they won't do anything because they don't have the activation energy, the energy requirement to get over the hill. We'll see an example of that in a second. But if they have enough kinetic energy, they slam into each other and that transfer might actually happen. So we got to imagine those collisions. Now, what is an elementary reaction? We've learned about reactions, but what is an elementary reaction? An elementary reaction, and sometimes you need to be told this, that it is elementary, is a reaction in which the reactant molecules must actually collide and react in a manner according to the stoichiometry. So, an example. If one molecule needs to collide with another molecule, the reaction would be first order in both, because both of those molecules are important. You have to have one of each, they hit, they collide, and without one or the other of them, the reaction's not going to happen. So they're very important to that reaction. If one molecule needs to react with two molecules of another, the reaction would be first and second order respectively, and third order overall. Because there's two of the one molecules, those are doubly important for the collision. And if you don't have both of them, then you wouldn't have the reaction that you're aiming for. If three separate molecules of separate species need to collide all at the same time, and this is rare, by the way, the reaction would be first order in three species and third order overall. All right, so that's a lot of words for something like this. Now take a look at this. This is a reaction. Here's the NO2 plus CO making NO and CO2. There is an energy hump. If you haven't talked about activation energy yet, it's coming up later in the unit. But there is a certain activation energy that you have to overcome because being in this sort of middle state where it's not the products yet, but we're not the reactants anymore, it's kind of a high energy situation, that's a transition state. And so to get over there, we need to actually collide in the proper orientation with enough energy to do so. But because this and this have to react with each other, you can actually write the rate law based on what we call the molecularity of the reaction. What two reactants are there? They're both super important, so they are both part of the rate law. Rate equals a constant times the NO2 and the CO. And if we presumably doubled one of the concentrations, we would double the rate. And if we triple the concentration, we'd triple the rate. They're first order in both. Okay, here's another example. We have a hydrocarbon molecule here. This is an ester reacting with an OH. And you might agree by looking at this, well, both of these molecules are pretty darn important because without this, we're not going to have a reaction. Without this, we're not going to have a reaction. So if you're ever asked to write the rate law, hopefully the question would tell you that it's an elementary step because then you can say, oh, I know what's on the left and I can write the rate law based on those two things. And there's one of each, so first order in both. Okay? And that's the big takeaway here. If you know it's elementary and those molecules have to be there to collide with each other, you can write the rate law depending on their stoichiometry. Usually it's a 1-to-1, sometimes it's a 1-to-2 ratio, and so on. So here's a multi-step mechanism. We're going to learn more about mechanisms in a couple sections. But step 1, we can imagine a bromine and an NO reacting to make this guy. Okay. And in order for this guy to be made, these are both important. So that's an elementary step, and we can write the rate law based on that. And then this guy turns around, reacts with another NO to make these two guys. And again, these two are going to be important because without one or the other, reaction doesn't happen. So it is an elementary step, and we can write the rate law first order for everything on that page. Let's get into a couple of questions. This is a very typical type of question. We have step 1 and step 2. Later on, we'll learn about putting them all together. But which of the following gives the rate law for the elementary step 1? So we're told it's elementary. Yay, that makes it easy because then I can look up here and say I have one of those, and I'm looking for the one that has one of each of those. And so we end up with H2 and ICl being letter C for that one. Okay, you try one. This is not a multiple choice question, but it's similar to something you might see. What are the rate laws for the elementary steps that are above? Take a moment and pause the video and write what you think the rate laws are. Okay, and if you wrote these two rate laws, there's actually two different ways to write the first one. But the first one involves an NO2 reacting with another NO2. And that means that's doubly important. So I have one of each of those, but since they're the same things, I can actually connect them and make it NO2 squared. So it's a second order with respect to NO2. And the second one has an NO3 and a CO, just one of each of those. And so it's 1-to-1 ratio. And like I said, we're going to do a couple of episodes on full-on reaction mechanisms. We're going to actually look at this one again and find out why the overall reaction, this one, actually is second order with respect to NO2, even though there's only one of them actually there. So stay tuned. Okay, let's talk about that last part of the learning knowledge for this episode. We have a couple of steps here. ClO2 reacting with fluorine to make this. This fluoride, this fluorine atom turns around and reacts another time to make this, and the overall reaction is this. So the overall reaction is 2 ClO2s reacting with an F2 to make 2 ClO2Fs. Why is this unlikely to happen in a single elementary step like the overall reaction? So these are elementary. Why isn't this an elementary step? Well, it has to do with the fact that collisions involving 3 or more things all at the same time are very rare and kind of unlikely to happen. So for example, we could imagine one of these ClO2s reacting with a fluorine, and they bump into each other. There's just one of each, so they collide, and we can imagine that that would be pretty common, actually, and most likely successful. We might imagine the same two molecules colliding in a different orientation that might not be as favorable, so maybe a little less likely. But let's go down here. The odds of 2 of these reacting in the perfect manner and the perfect orientation with the perfect amount of energy with this guy here, 3 molecules colliding together, It's not very likely. And so those are pretty rare and you're not going to see them that much. You might be asked questions, though, about why they're not that common. So, for example, let's do a common reaction. Two hydrogens reacting with oxygen to make water. Okay? And it's like the first equation that we all start with trying to balance. So we get 2, 1, and 2. And this reaction is very unlikely to happen where two hydrogens and an oxygen all magically converge on the same spot and put out two water molecules. Not very likely. What's more likely to happen, and you don't have to know this for this, probably for your AP exam, but you have to start the reaction with a little activation energy. And what happens, it happens in several steps, not just one step where all the collision's happening. First, the hydrogens break apart. Then one of the hydrogens reacts with an oxygen to produce an OH radical and another oxygen. And then at some point, that other oxygen picks up another hydrogen, and it's kind of like a stepwise thing. You got to break one apart, have it react partly, break another one, have it react partly. And it's a sort of a longer step process. Each one of these would be an elementary step, but the overall process is unlikely to happen in one step. And this is very similar to an AP Chem FRQ question that I've seen over the years a bunch of times. I just picked a complicated redox reaction. I'm thinking in particular of a couple FRQs that have similar reactions. And here's the reaction: 2 permanganates and 5 bisulfites and a hydrogen react to make these guys over here. And a student proposes that the above reaction occurs in a single step. Do you agree with the student? Why and why not? So you want to be careful when you get to a question like this, where you're being asked about whether it's a one step or not. Take a moment, pause the video, and see what you would formulate as your response to a question like this. Okay, and if you were paying attention, good job. And you notice that there's 1 molecule, 2 more, and 5. That's a total of 8 molecules. Imagine this happening in one step. You'd have to have 8 molecules converging on themselves in the perfect orientation and the perfect ratios to just smash together all at once and then produce 8 more molecules on the right-hand side. And that's very, very unlikely to happen because you just have so many species that need to collide in the appropriate way. So if you said something like that on your FRQ answer, then congratulations. Well, that's it for this episode. We're going to build on this in a couple episodes when we do reaction mechanisms, but I hope you found this helpful. Send me questions in the comments if you have them. And in the meantime, happy studying and have a great day.